so if you look at the Earth on the surface, we have the Pacific Ring of Fire, right? That's on the Pacific here, and this subduction girdle is bisecting the mantle in two domains. So on the right you have the Pacific domain, and on the left you have the African domain. Okay, and what's interesting with the core mantle boundary structures and the surface structures is that each mantle domain has his own Lsvp or his own superplume. So we see that we have deep structure and like shallow structure, but they seems to be connected. So the question, and this is like the $1 billion question, is the nature and evolution of the Lsvp or the superplumes, and what are their link with the plate tectonics. So do these structures deep in the mantle are linked to what's going on the surface, right? And this is what I want to answer. This is what I want you to understand. So before we go further into that subject, so just some definition to make sure that we know what we're talking about. So what we want to know if there is a link between the supercontinents and the superplumes, right? So first, what's the supercontinent? So for those that are not familiar with the concept, there is a pretty broad definition by May in 2012, which said that supercontinent consists of at least 75% of the preserved continental crust prior to initial breakup. So this definition is based on what we know about Pangaea, the last supercontinent you have in the right. So 200 million years ago, this is a reconstruction of the supercontinent with I'll try to find this. Sorry, I'm trying to find a way to pointer. Does the pointer working? Yes.
Yes, go ahead.
So, okay, sorry. So here you have Pangaea. So this is the supercontinent Pangaea, and you have the subduction girdle of Pangaea here. So Pangaea is a supercontinent according to that definition. On the other hand, if you look at Gondwana 400 million years ago, Gondwana, which is here, is not a supercontinent because it's only 50% of all the continental masses, right? There is another definition you can use to define what a supercontinent is a paper newly published by Murphy et al., which is also a co-author of the study. It said that supercontinent must influence mantle circulation in a manner that triggers the next stage in the cycle. So what does it mean? It means like supercontinents should be big enough to influence what's going on in the mantle. And using that definition, Pangaea is still a supercontinent and Gondwana is not. So we're going to stick with this definition for supercontinents. So once again, for those that are not familiar with that, there is several supercontinents in the Earth history, right? And a supercontinent is defined by the supercontinent cycles, which is the assembly of the supercontinent when all the masses getting together. The tenure of the supercontinent, when we have the maximum packing, when everything is together, and then we have the breakup. The breakup is just when like the continents start to drift again. Okay. And we have the Pangaea, the last one we know very well. We have Rodinia, fairly known, and then we have other continent, the Nuna, or some people call it Colombia, and probably maybe another one which is known as Kernoland, or this one is very controversial. But what is very important is the supercontinent cycles is it's like episodes of assembly tenure breakup, which take between 500 to 600 million years. So we have cycles of having supercontinent forming and dismiss of supercontinent. So this is the definition of the supercontinent and the supercontinent cycles. When we want to understand the link between supercontinent and superplumes, we need the definition of superplumes. So as I tell you just in the beginning of this presentation, the superplumes, they are the region of thermal anomaly in the mantle, and they are the main source of the hotspots and a large igneous province through time. So back again to the tomography at 2,800 kilometers, we have the African Lsvp here, or called the African superplume, and the Pacific superplume, African Lsvp. And on this map, I have represented the major hotspots and LEAP today, okay? And you see that they are closely linked to these major structures. Something also very interesting with this Lsvp. So you see Lsvps and superplumes, they are within each mantle domain, Pacific domain, African domain. And there also are what we say, they are antipodal. So this is a very nice animation from the Quanta magazine. So they did this animation using the data from Kota et al. 2016. And you see the Pacific and the African Lsvps. And you see that they are very perfectly antipodal. Okay, so they are the opposite to each other on the core mantle boundary. So these large low shear velocity province, Lsvps or superplumes, they are the major source for hotspot and plume. So this is really important. And how do we know that? So if we reconstruct, so this is the same. So this is the Earth. You have the thermal anomalies and you have the plumes represented here. And more importantly, you have the plumes, but you have the reconstructed lips, which mean the position when they were formed. And you have different values for the boundary of the Lsvps. And this work by Burke et al. 2008 say that every hotspot, major hotspot, and every major lips for the last 200 million years were formed at the boundary of the Lsvps. Okay, so these structures, they are very important to understand the volcanism for intraplate volcanism. And once again, so to continue to understand the link between supercontinent and superplume, so these guys, so Burke et al. 2008 and other people think that because for the last 200 million years, the lip and the hotspot were on the edge of the Lsvp, they assume that the Lsvp are fixed. Because if they were not fixed, so we should expect to have the hotspot and lips all over the place. And this is an argument that is on it's going on for years now about the origin of the Lsvp. Are they fixed or dynamic? So some people think the Lsvp, they are here from the beginning of the Earth. Okay, so they think they are primordial features that has been left from the accretion of the Earth. Okay, when you start to create the Earth, you're going to have like the magma ocean, you're going to have residue and stuff, and the residue of this stuff will be on the core mantle boundary and stay there forever. And then we control, as I say, plumes and hotspot and stuff like that. On the other hand, some people think they might be dynamic. So some people think that the position of the Lsvp and the when they're producing the hotspots is linked to other processes. And a major breakthrough has been done in 2008 by Li and Zhong. So they published a paper where they show, using geodynamic modeling, that you are clearly a link between what's going on the surface and what's going on at the core mantle boundary. So I will explain what this is about. So if you're here, so in figure A, you have the Earth. In blue are the downwellings, and in yellow are the upwellings. Oh, sorry. So the downwellings are the slabs, and the yellow upwellings are the plumes. So during the Archean, for example, we think we have what we call a degree N convection. So we have many different subduction, many different plumes. It's very chaotic. But at some point, we move to something more organized. We move to something which is called degree 1, which is you have a major downwelling and a major upwelling, right? And during this major upwelling, you will assemble the first supercontinent. When the supercontinent is assembled above this major, like in degree 1, so one big downwelling and upwelling, you have the supercontinent here. When the supercontinent is formed, you're going to have the subduction girdle all around the supercontinent. So today, this girdle is known as the Pacific Ring of Fire, right? Which is the legacy from Pangea girdle. When you have the girdle, so the slabs will go down to the core mantle boundary and will interact with it and will trigger the Lsvp. They will trigger mantle plumes, right? They will produce a plume below the supercontinent and an antipodal plumes, right? This is what we call degree 2. You have 2 downwellings, two upwellings, which is degree 2. And this is the actual state of the Earth. You know, we have actually two superplumes. And then you're going to have TPW to accommodate the change of the mass. Sorry. Oh, crap. Yeah. So this is purely geodynamic modeling, but this model predicts that you have higher mantle plume activity during the supercontinent breakup, and you have a close control of the Lsvp location by the supercontinent assembly. Basically, what it said is just where you have the supercontinent, you're going to have the girdle, and the girdle will trigger the Lsvp and the superplumes. So in that case, what you expect is to have episodic formation of mantle plumes through time. Based on these models, other people very recently tried to see if the hotspots are fixed or if the Lsvp is fixed. And a really recent paper in Nature Communication in 2019, the title is very interesting. So hotspots motion caused by the Hawaiian Emperor Band and the Lsvp are not fixed. So what they did in that paper, they show that in the right here, Hawaiian Emperor chain, the bending here, is not controlled by something. It's not controlled by, you know, like plate motion or whatever. It's just controlled by the fact that the hotspots are not fixed. So it's against the fixity of the hotspots. But more importantly, they demonstrate that the Lsvp are moving, and up to 13 millimeters per year, which is not, you know, which is not low. It's very important. So you have all the Lsvp are moving. So based on the present day record, but this is show us that actually we have a motion of the Lsvp. What we want to understand is what's going on in the past. We know with the supercontinent cycles. We have published a couple of papers in the past year, I would say, which show that we have a link between the formation of the plumes and the supercontinent cycle. So first paper by Hamed Gamal Eldian, which is a PhD student at Curtin. He showed that using global geochemical fingerprinting of plumes, that the intensity of these plumes through time is controlled by the supercontinent cycle. I will explain more in detail what he did, but basically he just took all the data from basalts from the geological record and analyzed their compositions, and we have a bootstrapping of this data to have a complete record of the mantle plume through time, and we see that we have plume intensity higher during supercontinent assembly. Another paper I published myself in Geology, where this time I was looking at the geological record of the Oceanic mantle plume, so the Oceanic plume record, so in the ophiolites. And what we show that we have more Oceanic plumes during supercontinent breakup, which is also in agreement with the model that when you have supercontinent trigger the Lsvp below the supercontinent and on the opposite side. So the geological and geochemical record of the mantle plume suggests a strong relationship between the supercontinent and the superplume. So here are the main results for these two papers. So Nature Communication 2019. So what you have here is the composition for what's going on. The composition for the magnesium, nickel, and chromium in the basalts. And what is shown that this is the delta MgO in the record. So basically what we are looking for increase in magnesium, nickel, and chromium in basalts, because magnesium, nickel, and chromium are linked to the temperature of melting, right, in the basalts. So when you have a positive delta MgO, you have more MgO in basalt at the time. When you are delta MgO negative, you have less MgO in the rocks. And when you do that for the entire record for 3 billion years, you see you have like a positive anomaly for MgO, nickel, and chromium during the assembly and the tenure of the supercontinent. So this is a really important results that show we have a clear link. And this is my geology paper in 2020. What I did is just having the Oceanic plume record compared to the continental lip record, and we use some statistics to deconvolute this signal to see if we have cycles. And what we show that the continental lip have 600 to 500 million year cycles, which is pretty similar to the Oceanic record, and it's coincide for the OLIP and CLIP, so oceanic large province and continental large province, and it's coincide with the supercontinent. And unfortunately for the oceanic plume record, we're only limited to the last billion years, because then less ophiolites and signal is blurred. So we have a couple supercontinent and superplume events, and now this is what we think. But then what we have now is just the supercontinent and superplume events that predict direct feedback between the Earth mantle and the lithosphere, the plate tectonics, right? So if it's true, if we have a link between the top of the Earth, so the continent, and the deep mantle, we should see a connection somehow. We should see evidence for interactions. So to see these interactions, what you can use, and you can use the isotopes, because the isotopes can be used to fingerprint the composition of the mantle at different places on the Earth when you're studying the MOBs or you're studying the OIB. And this is not a new idea, basically. So people are using the isotopes to understand the heterogeneities in the mantle for a long time. So this is the three main papers that are, like the core of how we understand the mantle, how the mantle is working, and how the mantle is heterogeneous. The first paper is by Dupré and Allègre, 1983. And in this study, Dupré and Allègre, they just measured the lead and strontium isotopes in a lot of OIBs all over the place, right? And Art in 1984 used this data and tried for the first time to see if there is a pattern, like in the location and the isotopic anomalies. And he sees something he called the Dupal Anomaly. Dupal because it stands for Dupré, D-U, and Allègre, I-L, Dupal Anomaly. So how did they find that? So basically what they show, these three papers, they show that you have in the isotopic diagram, so this is 206 lead, 204 lead, 207, 204, and 208, 204. What they see that all the northern hemisphere basalts are on a straight line, right? And all the basalt from the southern hemisphere, they are, in general, so the basalt from the southern hemisphere here, they are above this line. What is this called? The Dupal anomaly, right? So in the 80s, sorry, we already knew that the mantle is heterogeneous, and it's not random heterogeneity, it's a northern-south heterogeneity. So it's an hemispheric heterogeneity. The northern hemisphere being kind of normal, and the southern hemisphere being, like enriched or basically different from the north. And at the time, what they did, they just say, okay, so what happens in the southern hemisphere? And at the time, the knowledge about supercontinent and plate tectonics, we know that Gondwana was there, and they hypothesized that something happens during breakup of Gondwana, like during breakup of Pangaea. I say, oh, maybe the lithospheric mantle of Gondwana were sink into the southern hemisphere mantle, and then control the composition of these basalts. So Dupal anomaly is something very well known now. A lot of people are using these terms and this signification. And the story become more complicated. And this is funny because it's right away after these three papers been published. Castillo in 1986 in Nature showed that the heterogeneities in Dupal is not homogeneous. Basically, that's the funny thing. So what he did, he just reprocessed all the data. And what he showed that below the line, so the southern hemisphere, so like within the Dupal anomaly, you have another anomaly, which he called the South-Pacific isotopic thermal anomaly. So what they say here is just, okay, we have heterogeneity within the heterogeneity, the northern hemisphere being more or less homogeneous and the south being kind of a mess. And since then, the end of the 80s, people try measuring every different OIBs to understand what's going on. So this is like the recent papers, 2017 and 2018. So both one paper in Nature here one paper in EPSL. They just look at the composition of all different OIBs in the world, right? And what they see is there is heterogeneity everywhere. But by contrast with what Hallegre and others and Art see, there is no clear, like northern, southern border or whatever. So the message starting to be more complicated. So we know that the matter is heterogeneous, but we still don't understand what's going on. And why is that? It's because if you look at the lead isotopes in the different domains, African domain and Pacific domain, from the OIB here and the MOBs here, you see that everything overlapping, right? Everything is pretty much the same signal. And when you look at the OIB, which are deeper sourced, so we think most of the OIB can sample the lower mantle when the MOBs is sampling the upper mantle. We see that there is no major differences here. Because when you look at OIB and MOBs and you think that everything is the same, then you don't know what you're looking for. And that's the main problem with the isotopic. So we see on the surface, but we don't know what's going on down below the mantle. So some people try to characterize the origin of the OIB. For example, we know the OIB can sample the lower mantle, but Coutinho et al. Showed in 2003 that you have three main type of hotspots. You have the tip 1 hotspot of tip 1 that's down below to the core mantle boundary up to the surface, producing hotspot track. You have the hotspot tip 2, which are sampled by the super plumes, and you have hotspot of tip 3, which are just the upper mantle, right? And among these guys, you have the mid-ocean ridge that just sample the most shallower part of the mantle. So when you want to understand what's going on in the mantle, in the deep mantle, the deep connection between the core mantle boundary and what's going on the surface, you need to focus on different type of rocks. Basically, what you want to look at is the hotspot of tip 1 and hotspot of tip 2. So in 2003, Coutinho just defined a list of different criteria and try to give us an insight about what are these what plumes come from deep and what deep plume come from not deep. And using new detected plume, using, for example, tomography, you can see if the plumes are anchored to the core mantle boundary or to the lip. So what we did, so we used Coutinho and we decided to filter and to update that list, right? So to understand what's going on deep in the mantle, you need to only focus on the plumes that sample the core mantle boundary, could sample very close to the Lsvp. So updating the list from Coutinho, like 10 years after he created this parameter, this criteria, using new tomographic data, the most recent one, using the new isotopic composition, we come up with that map, which is a combination between the Lsvp and the plumes. And on that map, what we show that the major plume we have here, we have like 18 major plume products. Only eight, yes, can be considered without ambiguity to be deep sourced. Iceland, La Réunion, Tristan da Cunha, Kerguelen for the mantle, for the African domain, Louisville or Ontong Java, Easter Island, Galapagos Island, and Hawaii for the Pacific domain. The rest of the hotspots, they are ambiguous. We don't know exactly what they are. For example, if you take the case of Samoa Island is the best example for enriched basalt in the Pacific. But the problem with Samoa is that you have plume interaction. And if you look in this diagram, so for lead isotopes, so this is also lead isotopes, and this is strontium, sorry for these figures, you see that in blue, you have the Pacific data, and you have here the Samoa. And so you see that it's very different. It's because you have plume ridge interactions. So using this, what we decide to do is just to collect the data from the good hotspot, and so the deep hotspot, and compare them to the non-deep hotspot. So what we do, so method we use in the paper, so we just collect all the data we have in the big database from online, so GeoRock, Earthscape, and basically what we select all the rocks for which we have the major element, the lead, and the strontium and neodymium isotopes, and we select only the one with basaltic composition, so SiO2 from 40 to 50, and potassium and sodium below 10%. With that, we end up with 6,030 samples, and just selecting from our criteria, we have the deep source OIB and the other OIB. We have a quite significant number of rocks. But once you have that, you need to be very careful for what you're doing. For example, if you look at Kerguelen is one of the deep plume. The problem with Kerguelen is we have interaction with continental rocks in the early history, because Kerguelen is known to be the plume that breaks up Gondwana. In that diagram, again, lead isotopes, you see that some part of the data are really enriched because of the interaction with the lithosphere in the crust here. So what we do, we just selected the rocks for which we have unambiguous oceanic composition, and we excluded the older one that are more ambiguous with continental and crust interaction. So we did that for every plume. So we investigate each deep plume to see if there are ambiguity and if we have some time like interaction or something weird. And using that, we end up with, for example, in the lead isotope, we end up with the African domain deep plumes here in the left and the Pacific in the right. And by comparing this data, just by the eyes, it's very complicated because it seems that everything is, like the same. So what we do, we decided to use like statistical representation. We use the channel distribution of the data. So basically using a MATLAB script, we use the channel distribution of the data, and we try to represent them as where are the maximum of the data. And when you do that, you clearly see on these two diagrams that the African domain is very different from the Pacific domain for different isotopic systems here and here. So by filtering by mantle domains, by filtering deep versus others, and by using statistical distribution, we are able to show that the African domain is very different from the Pacific domain. Now, the main question is, why create this difference, right? How we can explain why the Pacific domain and the African domain is different. So we expect that for the link between the supercontinent and superplumes, but we need a process to understand what's going on. Doing some just geochemical modeling, very rough, very simple geochemical modeling. So we see in that diagram here for the African domain that the African domain lies between the prima, which is like the normal mantle, and the enriched component, especially the UCC, which is the upper continental crust. So what you can do, you can model what is the evolution of the continental crust and the normal mantle through time. So I started a model at 2,500 million years, and you make evolution of the mantle. You can do the same for the crust. And what is interesting is this gray area here is the representation of the mixing here between the continental crust and the mantle. And most interestingly is you have an age that come up, which is 700 million years. So this is 700 million year mix between the mantle and the crust here and here, right? So we can explain the composition of the African domain by a mixing between the mantle and continental crust, which is weird because we are right in the middle of the ocean with these OIB and LIPs, right? And we excluded every interaction with the crust to make sure that we're seeing deep signatures. And most importantly, it works in different diagrams, in different isotopic systems. So we have something happening at 700 million years and today. So what happened during that time? So during that time, we had the breakup of Rodinia and the assembly of Pangaea. So most recent research showed that from the first supercontinent Nuna to Pangaea, we have a change in the way of supercontinent breaking up and assemble. From Nuna to Rodinia, we have only introversion. So when you have this new supercontinent Nuna breaking up, the breakup is not complete, right? Just imagine like a failed breakup, and then Rodinia would just assemble on the same place. On the other hand, when you go from Rodinia to Pangaea, you have a very complete breakup. Basically, you're gonna just have an extroversion, which means that the supercontinent Rodinia will break up and Pangaea will assemble on the other side of the Earth, right? So a way to represent it is that diagram here. So if we are here, we have Rodinia. So this is a cross section of the Earth. You have Rodinia here. We have the girdle that trigger the super plumes, and then when you have the breakup, you see you're gonna have the continent moving on the other side of the Earth here. And doing so, you're gonna have a lot of subductions that will bring a lot of sediments to the mantle domain below the formation of Pangaea. Then you're gonna have the girdle of Pangaea here, and you are gonna produce super plumes that will break up Pangaea and being the source of most of the OIB we see on the African domain. On the other hand, nothing happens in the Pacific domain, and so the OIB and the lips here are gonna be devoid of continental crust mixing or contaminations. So when you go from Rodinia to Pangaea, you have extroversion and you have massive input of sediments through subductions when you have the assembly of Pangaea. And if you put that into context of the reconstructions, this is a figure from the last figure from the paper. So if you are here, you see you have like Rodinia breaking up, and the internal ocean of Rodinia is the future Pacific domain. And then you have the super ocean, Merovoi, which is the super ocean of Rodinia, which is the future African domain. Then when the breakup is being complete, you're gonna assemble, Pangaea. First you assemble Gondwana, then the other things. And then you're gonna have the supercontinent Pangaea assemble above the African domain, right? And you're gonna have the subductions all around that bring sediments to the African domain. Here in this subduction girdle here, you see the polarities will pollute, we can say that, or contaminate the African domain with sediment from the continent. And then you're gonna have the breakup, and you're gonna have the Earth how it is now with the mantle domain, the African Lsvp, with different compositions. So this is the main conclusion of the paper. So the paper here, so this is two quotes from the conclusions, and this is a beautiful way to show how it works. So first conclusion, the subduction polarity associated with the supercontinental cycles and superocean evolution can best explain why the African mantle domain is contaminated with continental crust material, whereas the Pacific mantle domain has been protected from such contamination for the past 600 million years. Then the deep mantle geochemical dichotomy, because now we have a dichotomy between the West and the East, show that the true mantle domain, including the Lsvp, may have been geodynamically and chemically coupled with the supercontinental cycle, then suggesting a dynamic instead of the stationary nature of the mantle structure and composition. And that's the end of the talk. Thank you very much.
Okay, great. Thank you very much, Luc. And now it's the time for questions from the audience. Yes, okay. It's good.
Yeah. Yes, exactly. So actually, if you look at the introversion extroversion hypothesis from Lee's entire paper last year, so which is called the super ocean cycles. So basically, what we think is the next supercontinent, so what we call it Asia, will assemble on the African domain. So basically, what's going on? So we're gonna have, so Pangea is supposed to have an incomplete breakup, and then we just assemble again above the African domain. So we think that the Pacific domain will remain the same for the next stage. Is that answer your question? No worries.
Okay, let me ask a short question. I think in your georock as well as earth chemistry data that you show that some of the OIB, you categorize them in the shallow source and some of them comes from deep. So may I know that what's the threshold that you separate them into two groups? Since from the geochemical signature, we could not directly tell the depth that which it comes from, which geochemical signature is indirect of showing the source of OIBs. Yeah, go ahead.
Yeah, so that's the tricky one. So we know we have to filter the OIB, and there is no clear answer because tomography is one thing, and then the resolution sometimes is not that great. So what we decided to do is just to use a bunch of criteria. First criteria, so it's based on what we think are big plume from the deep source. So one of the criteria, we think that each super plume or deep plume, sorry, should start with a large igneous provinces. So if you want to produce a large igneous provinces in the ocean, for example, you need to have a high heat flux from the mantle. So, and we think that, and models show that you only can do that from very deep plumes. Then when you have the sleep, because the plume will be very strong, you're gonna have an hotspot track, right? So this is the two first criteria. So each plume should start with a large igneous provinces, and you should have an hotspot track. First, then we look at the composition. So what we want is deep stuff. So to get deep stuff, you know that we can use some geochemical information like helium isotopes. So now it's well accepted that only deep plume will sample very primitive helium isotopes or very high helium isotope ratios. So this was another criteria. Like, let's see, we need have high helium ratios. And then another important criteria and is the fact that now okay, which is the I lose my focus. Oh yes, and the tomography. So in tomography, what we did, so we use we use several catalogs of tomography, and the idea say, okay, if we have the most accepted catalog, there is 3 catalogs now. I have the reference somewhere in the paper, but one paper from French et al. So I think it's 2015, and the other one is maybe Bosch or something in 2002. So this one are very well respected studies and like very thorough study. The thing is, if we can have the plume connection from the surface to the core mantle boundary for 3 plumes, for the 3 catalogs, then we can be pretty sure it's deep. So this was our criteria, the main criteria we used.
Okay, although some more, like say, combined evidence from noble gas as well as tungsten having isotopes, like the correlation has been shown by University of Maryland group. It's also very strong, but we have very limited data on tungsten having isotopes. So, but anyway, that's good. Okay,
just to talk about it. So I completely agree that it's not the perfect way to define things, but only using tomography is not also a perfect way. So if we go to use only that was a discussion actually. This is why we have such a big group, because we had to develop a way to exclude and include stuff. And for example, we have 2 plumes that has been controversial, like Galapagos and Iceland. For example, Galapagos, we think that the leap is the Caribbean leap, right? So, but we don't have a very clear hotspot track. Or ice is also problematic because is there a high hotspot strike? It's not really sure. Do we have a leap? It's not very sure, but we have the highest helium ratios there, and the tomography is very strong. So that's part of the method section in the paper. We have a good discussion about each individual plumes to explain why we integrate them in the deep, or the other one we say, oh, we can't be sure. The same for Samoa, for example. Samoa is very special because it's a clear subduction plume interaction, but in the same time you have very high helium ratios, right? And in the same time it's very enriched. So what are we? This is complicated. This is Samoa, for example, is how I can say that. Yeah, it was a problem. This is why in the paper we say, yeah, where Samoa should be a deep one, but there is so many problems, so we can't say 100%. We can't be 100% sure that what we're looking for is deep stuff. I hope I'm clear here. Sorry.
Okay, thank you for your answer. It's just a comment. Yeah, I think a lot of what you said was incorporated into method, although I did not read into detail. But your method section in the Nature Geoscience paper is probably one of the most extreme methods I've ever seen. It's a method mainly talking about the data criteria rather than, for example, more of the detail of the calculation. So it's a very interesting method section. By the way, it's just a comment. Yeah, we have other attendants to ask questions. So here is a question from Juan. I will read the question for him because he could not open his mic. His question is: the Iceland belongs to the African dome, but compared to the other lips from southern hemisphere, there's no anomaly on its isotopic composition. So what is your comment, or what do you think about it?
That's a very sharp comment. I mean, I appreciate it. Yes, exactly. So if you look at the diagram here, you see that Iceland basically is around here. Okay, so that's also been something that has been discussed with the reviewers many times, and in the group as well. So we don't have a clear answer about it. I can say that. So so the thing with Iceland, if we go back to the thing is Iceland. Some people would argue it's very far away from the Lsvps. Then maybe the mantle is I can say that we're not saying that the entire mantle domain is governed by. We should see I would say that we should see this enrichment everywhere, right? We might have some place that has been preserved from such things. For example, Iceland is far away from the Lsvp in the north, and most importantly, if you look at the geology and the paleoconstructions, most of the subductions and the collisions that could have bring the sediments when you have the assembly of Pangaea, Gondwana first and then Pangaea, occurs in the southern hemisphere, right? So that's what we argue in here. So we argue that Iceland might be something preserved, maybe because it's so far away from where the contamination occurred or something like that. That's the most plausible answer for why Iceland has the primitive signatures within the African domain. Does it make sense?
I don't know. Maybe Juan could type to see how satisfied he is about your answer. I have a question that is not directly relevant to what you do, but it's something related to the topic. So within Lsvps, the low velocity zone is not homogeneous. So which people, seismology groups such as that Leakage group, that they identify several zones that they call the ultra low velocity, not the ULVZs, but the mega low velocity zones, and not those tiny small ones near Earth core mantle boundary, but a certain proportion of Lsvps that has a particularly low acid velocity zones, mainly, let's say, probably in the bottom, at lower half of Lsvps. So from your perspective, so how could let's say, how is that related to the supercontinents? Although it's just a part of the that's a more detailed features for Lsvps. Do you think, or what is your comment about this type of structures and its geochemical consequences could be? It's just an open question.
No, that's very nice question actually. That's also something we are talking about in the group. So yes, so just to back up a bit, so what I wanted to do with this study as well is just to show that the Lsvp shouldn't be treated as a whole. You know, like in modeling and stuff, people just putting the Lsvps and they assume they are the same. Here we say, oh, they might have a different history because the interaction with the supercontinent and stuff. And now there is more and more study that say that they might be heterogeneous, right? And some people think they might have some layering, for example. So I see a very recent paper in Science Advance. They show that the border of the African Lsvp, I think it's on the, there is a hotspot track, the Walrus Ridge, something, a study about Walrus Ridge that show that the border is maybe more IMU and the inside is more EM1, and they might have like layering in the Lsvp. And one of the questions we have here, so we don't know what they are actually, the Lsvp. Are they primordial material? Are they a mix between primordial material and slabs? Slab graveyard going on. So how much material can enter in the Lsvp? How much material can outside the Lsvp? That's very open questions, and that's something we are going toward now. So we want to see if there is a way to see the, like the structures and the heterogeneity of the Lsvps. But for now, I don't have any answers. But that's the future.
Okay, so here is another question from the audience. I'm going to read it for Hao, and from Curtin University actually. And he has a question: is that does Gondwana supercontinents influence the mantle, and while the Pangaea supercontinent influence the mantle? So why? I think it's why that's Gondwana continent did not affect the mantle, but the Pangaea supercontinent affect the mantle. So how to understand that, and then what are the evidences?
So from my understanding and from the geodynamic modeling and what we are doing here in the group, so Gondwana is kind of too small to be to influence the mantle, because you don't have necessarily a subduction girdle as well on alongside Gondwana. So this is kind of controversial. So actually, some people think that Gondwana is just just going back to the reconstructions and the first slides, I think, just to. Yes. So when you see here, so the girdle is building up, right? And some people think that Gondwana was part of a Pangaea supercontinent, but we don't have any paleomagnetic evidence for that, right? So my understanding is Gondwana was not big enough to influence the mantle. And when you look at geodynamic modeling, you need like a critical mass of continent being assembled to trigger, like the subduction girdle and the degree to antipodal superpose. That's my understanding. But in the meantime,
okay, I'll insert one question. So what is the threshold for this mass?
Oh, this is an excellent question. I don't know, and I think nobody knows. That's what we are going through. So we want to understand that. So this is Murphy et al. 2020 papers. I'm co-authored as well. It's exactly what we're saying here. We are now working on what exactly is the threshold, and because the geodynamic modeling, you can have a threshold, but you need to also incorporate what we know about the supercontinent stuff, right? So the shape of the supercontinent, when you form the girdle, how long the girdle can survive, and stuff like that. For now, I can't say. I would say 75% would be the threshold, but I'm not 100% sure. I'm not sure if it's clear, but the thing is, we know we need a big enough. The geodynamic model is sure that's big enough, but the modeling is not how it works actually, right? It just gives you an insight of how the world should be, how the world not should be, but how the world could work.
Okay, here's another question I read from Juan at Zhejiang University. So he has another question, whether it is possible that the same OIBs in the Pacific Ocean, for example, Pitcairn Society, etc., that are sourced from the Lsvps or not? If possible, does it affect your model?
A very sharp question as well. So actually, if you look at all the OIB from the Pacific, yeah. So if you look at the OIB in the Pacific, except Samoa, which is could be an exception. So they still lie on the northern hemisphere reference line. Actually, that's what we can show in the supplementary material as well. So now, even if you take all the OIB from they are deep or not deep, excluding Samoa, it doesn't change the model. And it means that the entire mantle, so a lower mantle, upper mantle, or everything that has been sampled, are not affected by enrichment by continental sediments.
Okay, now we have Xiaoyan Gu from Zhejiang University going to raise a question.
Yes, I have a question. Is that the formation of African Lsvp can be accounted by the subducted slabs to be consistent with the geophysical observations? But as you discussed, if the Pacific Lsvp was formed only from the primal mantle antipodal to the African Lsvp, how it was generated to be consistent with the geophysical observations?
I'm not sure. The thing is, so you want to know if the Pacific Lsvp is more primordial, right?
Yes. It's
yes.
As you discussed. You said as you discussed, you think that the Pacific Lsvp was formed only from the primal mantle. If just from the primal mantle, how it's generated to consistent with the geophysical observations, because it is different from the surrounding mantle. Yes.
Yes. No, yeah, that's a good question.
Yeah.
Basically, so what the Lsvp is okay. Where again, just something to just a representation. This makes things easier. Coming, yes, here. So if you look at here, so the Lsvp here are this red stuff. So basically, what happens when you have the supercontinent assembled? So you have the slab, the girdle, the slab that pushing this layer to make it like more prominent below the supercontinent. Basically, what's the Lsvp are made of, we don't know, and I don't know. You know, probably it's primordial stuff. Probably not. I don't know. The only thing I know is just that the mantle domains that encompass the Lsvp, where you have this Dupal anomaly, can be, contaminated, right? And maybe we have things that going on into the Lsvps, but this has to be proven by, I think, seismic or tomography.
Okay, Luc. Okay. Yeah.
No worries.
Okay, Luc, I have a question.
Yeah.
And in some OIB from the Pacific domain, and you can also see some enrichment signature. And it should be related to some subduction events. How can you discriminate such subduction with the subduction related to the breakup, building and breakup of supercontinent?
That's also something we are working on. So there is a new paper that shows some ratios in the basalt can be. So the idea is just to track like a slab source from the basalts, right? So for example, we know that in Hawaii, a good proportion may come from a pyroxenite. What are these pyroxenites? We don't know. Okay, so that's also something we are trying to address here. So, but keep in mind that in this study, we are looking at the, we are using at the distribution of the elements right here in that diagram. So we know there is complexity, but we are looking at the main signal we are seeing. This is why we use the statistical distributions, the kernel distribution of the data. And certainly there is more complexity because the mantle is very complex, and there probably is some stuff in the Pacific that could explain this discrepancy, right? For example, in that diagram, we know that most of the rocks are here in the Prima mantle, but we have the Galapagos Islands, which are more enriched, like if there is more IMU signature in there as well. So we don't exclude that. The question is what it is, we don't know. So I'm pretty sure there is some IMU signature in the Pacific mantle. We have this IMU signature, like for Cook Austral Islands, for example. Galapagos is a good example, going toward the IMU signature. But what is IMU? So is this the subduction stuff? Is this the remnant of very early differentiation of the mantle? I don't know.
Okay, thank you.
Okay, Luc, so could you briefly explain it again about this figure? So it's not that the red circle or the red grids they are not the average. So could you explain again? I think it's explaining your supplements. Rather, could you explain to our audience that how did you get that number? Because it's not so obvious from people's eyes that definitely that's not the, let's say, more average that people could think of. That, and that's highlights actually the key points of your paper. So could you explain again?
Yeah. So the thing is, so in the left we have the African domain, in the right we have the Pacific domain for 206, 204, 207, 204, 208, 204 isotope systems, right? And when you remove these lines, you see that the Pacific, the African domain is generally more enriched, right? But there is a complexity here. So what we decided to do is just to use what we call, since it's basically it's just a 3D histogram, basically what we're showing here. So you use the distribution of the data. So where are the data distributed? So here. So basically in this red line here, the dashed line is representing the tenths. So it means like within this red line, you have 10%, you have 90% of your samples, right? But then you have the distribution, which is going toward these values here. So most of the data are concentrated here, but a fair bit of data are concentrated here and here as well. But more data are around here. The problem with these 2D diagrams, like lead ratios, so the data points just overlap with themselves. You don't see the density of the data. I see, this is what we wanted to show here. So we want to see the distribution of the data, and it's not a simple histogram. It's a kernel distribution. So it's just a statistical distribution of your data represented in a 2D space. Is it clear or?
Yeah, I think it's clear, and it is also hard to visualize in 3D. Even in 3D, you could do it better, but still, it will be very hard to see. I think that's my expectation.
Yes, that's the thing. So we were thinking of several ways of presenting this data, but it's not maybe a 3D diagram would help, but then how to find a way to make it clearer. So this is why we think that this diagram are fairly okay, because you see the clearly this point is very different from that one. So if you projected this one here, you should be here, and this one is here. But then you have the entire distribution of your data, which are spread across your diagram. So, but once again, what we are saying here, just not like they are completely different and they are like very distinct. It's just they demonstrate that the African domain is toward these values, more enriched than the Pacific, which is less enriched. That's pretty much what we are saying. But finding a way to represent this data maybe in a better way, if someone has a good idea, I'm taking it. No worries.
So more questions from the audience? Okay, if not, we will end our seminar today. And thank you very much, Luc Doucet from Curtin University, Australia. So thank you very much. And thanks everybody for participating in this seminar. Okay,
thank you very much for having me.
Yeah. Okay, have a good day. Bye-bye.
Bye-bye.